start.
Okay. Good afternoon, everyone. Thank you for coming. We are group 4 of Dr. Ting's Aero Design 2 class. Team members are myself, Jun Ling, Austin Borg, Harris Mahmood, John Erickson, Andrew Brennan, Kyle Stromberg, Jose Chavez, and
Brendan Hodes.
Brendan. Next. Okay, and so for our mission requirements this year was to create an electronically powered RC aircraft that can fly 3 laps around the flying field, around 7,500 feet in total within a time span of 5 minutes. And it has to land successfully and be able to take off unassisted. Certain other restrictions that we have to follow where it cannot exceed 8 feet in any dimension, and it cannot weigh more than 55 pounds. But other than that, we were pretty much given allowed to do whatever we wanted to do in terms of that, other than it had to be a fixed wing aircraft. And so with that, we wanted to do a high efficiency and high endurance plane, much like modeled after the U-2 spy plane. And we thought maybe in the end, we could also mount a camera for surveillance. And so that brings us to our preliminary design. So to begin, we had to create some initial estimations for what our final plane would look like, but just to get started. So we estimated around a gross takeoff weight of 7.5 pounds, and we used a similar structural coefficient from the Joker plane, which is a very successful RC aircraft that was created to be able to be 3D printed. And so using a lot of similarities from that aircraft, we're able to create our initial estimations. We used a very common metric for RC aircraft known as the wing cube loading. It would have a score of 9, which gives it a speed a little bit higher than that of a trainer aircraft. And the wing cube loading kind of just tells you what your flight characteristics of your RC aircraft will be. And using the wing cube loading, we were able to find our wing loading as well by finding out our wing size area needed. And we were also able to figure out our target speed and the Reynolds number at which we would test all of our airfoils at. Okay, and so going on to our airfoil analysis, we chose between 4 separate airfoils, the Clark Y, Clark Z, SD7062, GOE 389, and GOE 425, and these were analyzed at the Reynolds number as before. And it was pretty obvious just from our analysis, which we used on Excel Solar 5, that the SD7062 would be the best aircraft, and it was mostly for its better stall characteristics because it stalled at a higher angle of attack than the rest, and it had the highest maximum coefficient of lift at that Reynolds number of 230,000.
So for our wing sizing and performance, we chose a wingspan of 6.25 feet with an aspect ratio of 8.86. The taper ratio of the wing was 0.46, which yields a mean aerodynamic chord of 0.75 feet. The other parameters of the wing, such as dihedral, sweep, and incidence, were set to 0. This makes it easier to manufacture, and stability can still be maintained through airplane design as well as through pilot input. The other control surfaces, the ailerons and the flaps, those were sized and positioned through historical estimations with a 25% of the chord for the control surface chord size, and the ailerons would have a 50% of the total span, and the flaps would have 40% of the total span. This wing configuration yields a trim at 2.1 degrees alpha and a loading of 8.2 pound force.
For the servo attachment and design of the aircraft, we utilize CA hinges. The CA hinges are seen in the top right of the slide. They are paper hinges that are meant to be slotted through tiny slots located in the control surface and the main surface of the plane. What would happen is you would slot the paper in between those cracks, and you attach it using CA glue. and then you would attach the control surface onto that CA hinge, and then also attach it with another drop of CA glue, and you would constantly move the hinges as to allow it to have a free range of motion before it dries completely. And then control horns were used for the control surface attachment and control, as seen in the bottom right of the slide. These control horns were made out of basswood and were laser cut using a laser cutter. They were placed at variable distances along the control surfaces as to meet the length requirements of the control rods that were used for attachment from the servo to the control horn itself. Off-the-shelf control rods were used for the control surface connections. As such, that is why we required the control horns to be at different locations, as not all control rods included in the set that we purchased off the shelf were included.
All right, moving on to the conceptual design. First, we have the fuselage. This is what remains of the fuselage, sadly. But as you can see, it's all 3D printed, very lightweight. It is a 2-layer shell of PLA, very lightweight and cheap. And inside we have longerons and frames throughout the fuselage. There are more frames at areas of structural like jeopardy, like landing gear and wings. The cylindrical shape is minimalizing flow separation. And as you can see, there's no really sharp corners other than the empennage back here. And for the wing, where all the tails and wings come together. Other than that, yeah, it held up except for, yeah, for when it crashed. And then the tail. Empennage design is a traditional tapered configuration. Each of the tails are NACA 0012s. We use sizing volume coefficients to determine spans and root chords, and that's what we base the geometry off of. Sweep, we chose 15 degrees. And the control surfaces are 40% of the chord.
And then for our propulsion system, we powered everything with a 4-cell lithium polymer battery and a 50 amp ESC for our proportional control, which was connected to our main propeller. We used a badass 270 kilovolt brushless motor paired with an APC 10x60 propeller. Our main prop was located on the nose of our aircraft, and the motor and propeller combination achieved our thrust to weight ratio of 0.5 to 1 at 400 watts and 0.7 to 1 at maximum power. And these thrust to weights were calculated using our initial estimate of 7.5 pounds. They adjusted slightly between plane iterations as we'll talk about later, had to add weight for our first test flight, and were able to take off weight by changing our fuselage in our second test flight. And then for all of our electrical systems, we had the provided 6-channel transmitter and 6-channel receiver. And we ended up using 5 of those channels for our flaps, ailerons, elevator, rudder, and main motor. We had 3 metal 17-gram metal servos for our aileron, or 2 for our ailerons and 1 for our rudder, 2 plastic servos for our flaps, and 2 17-gram plastic servos for our elevator. And then into our proportional control, we had the 50 amp ESC and big lithium polymer battery, as talked about in the previous slide, and that powered our brushless motor.
So for the structural analysis of the wing, there's 2 load cases we considered. The first was the rapid deceleration that that would occur in landing, and the wing would feel that. So that was the first case. The second case was max speed and stall angle. We found the max speed and stall angle to be the more significant case. So for velocity or max speed was 55 feet per second, stall angle 15 degrees, and we had a weight of 5.21 and a maximum lift of 25 pounds. There we find like a lift over weight, which is around 4.8. So we assigned like a load factor of 5. We use a cantilever beam approximation and assume an elliptical lift distribution at the core to core where our spar was located. Our spar was made out of poplar wood, would have an ultimate strength of 3,200 psi. We calculated our maximum bending stress by our lift per unit span. We integrated that twice to get our moment, and our maximum moment would occur at the root, which is the equation right here. our maximum bending stress, which is the sigma normal that would be experienced at the top or bottom, depending, one would be tension, one would be compression, was 760 PSI. We designed for a factor of safety of 3, and our margin of safety was 0.404, which we we're very happy about because it was not over designed, it was just where it needed to be.
For our stability analysis, we assumed linear aerodynamics and we also assumed small angle approximations. Our pitch moment coefficient is summed up by the contributions of the wing, horizontal tail, and fuselage. In the equation, eta takes into account that the empennage receives lower dynamic pressure and epsilon is the downwash angle. The requirement for that coefficient is to be less than 1 for a stable airplane. The rolling moment coefficient has contributions from the wing and vertical tail, and the requirement for that one is to be less than 0. And the yaw moment coefficient takes into account the vertical tail and fuselage, and sigma in this case is the sidewash, and the requirement for that one is greater than 0. The way we use these equations was by choosing 2 values. So because roll and yaw are linked, there are only 2 variables we could like close a system of equations with. So we found a value of these coefficients in between a glider plane and a general aviation airplane, and we fix our pitch and moment coefficient. And then from these equations, we were able to solve up for where our aerodynamic empennage surfaces should be. And here are the coefficients where they're all signifying a stable airplane. So just because you have a statically stable plane doesn't mean it's dynamically stable. So the way you check for that is by doing a system of differential equations where your state variables are your velocities and your orientation angles, and the matrices A and B contain the aerodynamic and inertia information. So we used the most up-to-date iteration of our SOLIDWORKS file after we made the changes, and we use that in XFLR 5 to determine the eigenvalues. And the eigenvalues correspond to different flight modes where the real component, the more negative it is, the more stable that mode is. And from our analysis, the only unstable mode was found to be spiral, but this isn't an issue as many planes are unstable in spiral, and it takes almost over a minute to get around 1 degree of bank angle. The other concerning mode may be the phugoid mode where it's just barely stable, but the reason why we weren't too worried is because we were assuming potential flow assumptions, and in real life, drag is a lot bigger, and drag is one of the major sources of damping of phugoid, and that's indicated in our flight cases that we didn't really see any occurrences of much phugoid. So in general, we had a stable plane.
All right, moving on to manufacturing of the plane. First, we started dealing with the wings. So here is the remaining wing. The other one is not in as good of shape. So we used Ultracoat to wrap the wing, and this is a very cheap and lightweight option instead of 3D printing using PLA of the whole wing. So we decided to use this, and it is easy to cut into and make edits. So this is what we had to do for putting the servo motors in for the flaps and ailerons. And it was easy to wire it rather than having to worry about like editing, 3D printing, having to print whole new parts. That would really have slowed down manufacturing. The ribs in here are printed of PLA, and the spar in here is poplar, and the stringers are of balsa wood. And the flaps and ailerons are also just 3D printed. And basically the same goes for the tail as seen over here. The design or the manufacturing was done in the exact same process. And for the fuselage was entirely printed out of PLA. They had hatches, which were about 2.5 inches by 6 inches wide, so that we could provide access to the battery and bolting the wing and empennage to the fuselage. For the first design of the fuselage, there were none of the stringers or ribs that Drew previously mentioned. There were none of them in there because we originally planned to print bulkheads and put them in there and glue them in there. But we decided to change this design because we didn't have enough surface on the fuselage pieces to really provide a good way to glue them all together in a more reliable way. So we reprinted them all with little, basically ribs right at all the edges so that we can have more surface area to glue to. One thing that we should have done, it was probably include tabs like we had in the first time. We had little tabs seen right here to help with alignment. We should have included something like that for the second time around to ensure that they were aligned properly so that, you know, the tail wouldn't be at some sort of angle compared to the wings, which we had dealt with and had to cut apart and fix that. For all assembly, Loctite CA glue was used, and as seen here, and there were no issues with any holes for bolts or servos or wiring.
Here is our information on the landing gear. For our aircraft, we chose a tricycle configuration. This configuration is passively stable while on the runway. So while landing, the friction between the landing gear, wheels, and the surface of the runway will passively point the nose towards the center line. This, on the pilot side, requires a landing flare, nose down to make sure that the nose is securely on the runway. The rear landing gear, it is made out of aluminum sheet metal. It is secured to the fuselage using an array of bolts and washers to distribute the force along this area which it is applied. Internally, this is placed on internal bulkheads to make sure that forces are distributed through the parts of the fuselage which are designed to handle these forces. In the previous iteration of the aircraft, this was not the case, and the skin took the load and was unable to sufficiently carry those forces. Also included in the design is a tension wire. This is attached via poles in the landing gear. This allows the landing gear to maintain its shape upon ground loads and any other loads or impacts. The nose gear is attached to the front of the aircraft using shaft collars. This is a non-steerable nose gear, but as will be discussed later, the issues that may have been present due to this were avoided.
Great. So our next section is going to be the flight testing, which occurred at towards the end of the semester. So the issues encountered before our first flight, we did encounter a few select issues that would have been detrimental to the initial first flight. This included the lack of rotational restrictions in the front of landing gear. So as we discussed before, 2 shaft collars were used to secure the landing gear. This obviously does not restrict the rotational motion of the landing gear. So instead, as a fix to ensure that the landing gear does not rotate on that first flight, we epoxied the front landing gear to the fuselage, which as shown later through flight, proved to be a successful temporary fix, although not a permanent fix for the plane. The CG was also found to be too far aft in the plane. This was a product of a lack of prediction on our part for the overall CG of the aircraft before assembling. And how this was fixed was we included a ballast which weighed around approximately 13 ounces. It was comprised of 4 fishing weights and a 3D printed box which would house those fishing weights. These fishing weights were CA glued to the box. And that box had Velcro on the bottom, which would be attached to the top of the battery to ensure the most shift in the CG. And this shifted the CG from a static margin of 1% to a static margin of 7%, which we believe was a great help during our first flight and staying in the air properly. The rear landing gear was also improperly placed and introduced a slight wobble in the plane. What we mean by this is that the landing gear was not completely in face with the fuselage. The platform that the landing gear was placed over was smaller than the landing gear itself, which led to a wobble in the plane. How we fixed this was we placed CA glue on the landing gear itself to at least provide a temporary fix for its first flight to prevent wobble during takeoff. And then the rear landing gear was not made to the proper height, leading to a slight slant of the plane. The slant was towards the left. This was a simple fix. All we did was we took apart the landing gear and we rebended it to be the proper height to ensure a proper takeoff.
So for our first flight test, here's some of the weather conditions. It was a sunny day, but it was pretty windy. Sustained winds about 10 miles per hour and wind gusts of 18 miles per hour. It was a mostly successful flight. We did manage to do our 3 laps. However, in landing, our both front and back landing gears immediately broke. As mentioned by Brendan, it was incorrectly designed, the connection to the fuselage, because there was all the impact load was being transferred to the skin of the fuselage, which is not supposed to happen. We added bulkheads to fix that, as we're gonna mention in the next slide. The roll control was overly sensitive, and the takeoff distance, we actually took off like not towards the runway, like I guess perpendicular to the runway, and the flaps was able to help that too. We had such a short runway, but we were able to get off the ground because of the crosswind that we were experiencing that day. And we had a total weight of 6.68 pounds, obviously because of the ballast we added to the nose.
So after our first flight, we looked to some areas where we could improve, at least on the second flight, without doing any major changes to the currently intact fuselage. So first, we did some fuselage reinforcement via additional internal frames. This was done to ensure that the landing gear on a second landing attempt would not be able to push through the fuselage skin and make a failed landing. So instead, we, as you can see on the bottom right, we added 2 frames that were triple the thickness of the normal frames that are located along the platforms for the landing gear, and this would restrict the upwards force stressing the fuselage and hopefully be able to keep the skin intact on landing. We also, as you can notice, increased the platform area to uncover the entire new landing gear's top side. We also redesigned the rear landing gear, as you can see in the top right. Before, we had a small thickness with 2 mounting holes on the landing gear, and our redesign was we doubled the width to give more of a distributed load onto the skin when landing, and we included 4 holes so that we can incur less of a wobble and it can be a little more securely fastened to the airplane. And then we also moved the rear landing gear location such that the CG is roughly 15 degrees to the landing gear to help with takeoff and to help the elevators torque the plane upwards. Also, we extended the fuselage nose to move the CG location as a fix to not introduce more weight into the plane through ballast. The static margin was altered from 1% to 8% through this method. We did this by extending it by 8 inches. And additional hatch locations along the fuselage were also added such that you can access the wing a little bit easier, as well as access the rear landing gear in case something happens to it upon landing and we need to access it again to service it.
Here's our outcome of flight test number 2. On this day, the weather conditions were sunny with a sustained 4-mile-per-hour wind and gusts of 10 miles an hour. Overall, this was a good day for flying. However, the end result might not make one think of this. The plane crashed due to pilot error. The plane encountered a stall, and during the stall, there was loss of lift and the plane nosedived and crashed into the ground. This was due to spatial disorientation due to distance from the observer and the angle at which the plane was rotated. During this test flight, the plane weight was 5.89 pounds and had a thrust-to-weight ratio of approximately 0.7 to 1. These adjustments in weight and thrust to weight are due to these changes previously mentioned, where the ballast was removed and the design of the plane was adjusted to adjust the center of gravity without introducing more ballast to the nose. Next. For pilot feedback on these 2 test flights, the first test flight went well. The takeoff roll was short. There was both a a headwind directly into the takeoff path, as well as flaps on the aircraft. The combination of these 2 effects made for the takeoff roll to be very short and quick. During flight, when starting the turns in the pattern maneuver, there was sensitivity, especially in roll. During these turns, the high wind and the large aerodynamic surfaces of the wing allowed the aircraft to pitch pretty quickly and catch the wind, in one way to say. The combined wind heading into the wind and flaps made the landing approaches very controllable at low speed relative to other aircraft. This allowed for the approaches to be planned and come in very smoothly. For the second flight test, there was much less wind during this time. The takeoff roll was much longer due to the absence of this headwind. The flaps were especially useful during this case because otherwise there would be very little to aid in the planes taking off the ground. During this takeoff roll, because it was longer, the plane was able to accumulate a lot more speed. This speed allowed the rudder alone to control the direction that the plane pointed during this takeoff roll, which is why the nose gear was still usable despite it's not including a steerable mechanism. During flight, a constant pitch input was required. This pitch input was relatively constant due to the lack of wind and would be mitigated through the trim effect on the transmitter. In contrast to test flight 1, there was lots of wind gusts that were variable during this flight, and the pilot input was highly variable during flight test 1 as compared to flight test 2. During flight test 2, there were higher speeds encountered, there was less wind, so I did not ease as much on the throttle. These higher speeds during maneuvers also resulted in previously unseen effects such as flutter on the right or left aileron here. This is the particular aileron that fluttered. And these are the factors that were encountered in the second flight test.
All right, and that opens up us up for a Q&A.
Great job.
Thank you. Show my volumes.
Tom.
Hey guys, this is Tom Singer. I cringed at the picture of the crispy battery. I'm sure you guys cringed harder in real life, but you know, good job getting it up in the air.
Tom, do you have any
Let's see,
questions?
on hello? Can you guys hear me?
Maybe
Can you open
is there
the
volume?
chat?
Hello? Test 1 2. Test test. Test 1 2.
Should we
Can you hear me?
open the chat real quick? It seems like there's a message in the chat.
I'll do it in the chat. No, we cannot.
I don't mute. It's a red light.
Speakers. Check his speaker.
Is there a speaker on here, the microphone?
Probably not.
This is mute. Like, should I press this button?
You could hear us, otherwise.
Yeah.
I would have said something sooner.
That would have been.
Or in general.
She probably didn't.
I
I think it switched the speakers to the microphone as well as the microphone itself.
Oh, well, this red light is on.
I just means it's on.
Well, but it's right under the mute button. Should I press that?
I don't know. Tom isn't.
Can you guys hear me?
Yeah, he was.
Test 1 2. Anything? You guys hear me?
We better go ahead
Okay.
and fix this.
No, what if like we were on mute the whole time?
Well, no, if you were.
Then you
mute,
would ask the question.
you'd be asking.
You would have switched.
Oh, okay.
I have no idea.
Maybe can someone else join the Zoom call and see
Yep.
if they can hear?
I'm not. You're only going out with him.
Gotta run it back again.
Do you want me to reclaim host or stay co-host?
Yeah. The
The audio's working.
Yeah,
Right.
it's not good.
You're on mute. Dr. Ting, are you on mute?
Shouldn't matter.
What's it?
This is my.
So should I reclaim host or stay co-host?
I'd say. And you can still hear?
Yeah, I can.
Okay, so then the audio was recorded. Well, should have been, but you guys.
So here's, we can do, mute your thing and you can talk to the phone.
Test 1 2.
Okay, so I
Yeah.
just unmuted myself. Let's see, Mr. Tom, you should be able to speak now, and they can hear you.
Okay. Can you guys hear me now?
Yeah, they can hear you. They're just talking through my phone, so they're just gonna have to listen to you through my phone.
Okay. Excellent. Okay. So yeah, so I saw the picture of the crispy battery and I kind of cringed. I'm sure you guys did when it happened live. But congrats on getting something up in the air. That's an achievement. Let's see. So on slide 5, just a kind of presentation note, when you're showing the lift characteristics of your airfoil, it's hard to read, and I know Ting has called this out a couple of times on other presentations. We can kind of get an idea of if I sit close to my screen, I can get an idea of what the numbers are and what the axis labels are, but it's really hard to pick out which of those is your chosen airfoil, right? So I think if you can maybe highlight that a little bit better, and then explain why. In the SD7062 airfoil, we picked it because of this. Because to me, these look like very similar airfoils, and there's not really a strong reason for choosing one over the other. So I would encourage you to kind of present that in a little bit more understandable way. But that said, is there something that you would point to on these plots that said, hey, this is specifically what drove us to the 7062 airfoil?
So particularly on this plot, it was the higher coefficient of lift provided by the SD 7062. So I do understand, it's a little hard to read, but that would be the orange line on the graph. And we also believe that it had better stall characteristics after the stall point. It was less steep. So that kind of made us lean towards that airfoil in particular.
Okay. All right. Let's see. So on slide 13, when you started getting into the structural analysis, I really appreciated that you kind of detailed what went into the load case. You said, okay, we've got a G loading of 5 from this condition in the aircraft. That's good to see. And then you said, okay, so we've got our G loading. This is our lift distribution. So this is the moment at the root. And then what I think I was missing was how you get from a moment to a stress, right? So your max bending stress of 760 psi. What is that based on?
Oh, just use MC over I.
Okay, what cross section are you considering?
Circular cross section from the polar spar running through the quarter cord.
Okay, yeah. So I'd like to see that shown here on the slide. But that said, right, other than that one part of the chain, right, I think everything else was good. I like that you talked about, we've got a design factor of safety of 3. We've got a margin of safety based on that design factor of safety. So I think everything went well from a structures point here. I definitely would like to see a little detail of that joint, kind of the geometry of that joint and how the loads get into the plane. But I think what you got here is pretty good. On slide 19. So I was looking at this slide and I wrote down, man, I like the placement of the main gear. You said you set it right under a bulkhead. I like the design with the 4 holes as sort of a forward aft stability consideration. I wonder if you could have gotten away with 3, but I like it. And then we got ahead to the pictures, the aftermath of the first flight where you punched right through the outer part of the plane. I'm like, what the hell happened? I thought they put it right under the bulkhead. And then you explained that was a design modification. So I'm glad to see you kind of adapted and made initially a not so good structures decision and then fixed it and made a better structures decision. So good work with that. One thing I would ask here, looking at this, you did note that you widened the landing gear, right? So is there a reason the entire thing needs to be that wide, or could you have just widened it at the connection to the fuse?
It could be tapered towards the bottom of the landing gear, since most of the stresses would be occurring at the top near the attachment point to the fuselage. I think we opted not to do that for saving on time, but I do not believe it would be too much of a time.
We had limited time to remanufacture a new landing gear, and this particular second landing gear, there was some issues with the sheet metal piece I was initially cutting it out of, and I was just using the like sheet metal brake to cut whole lines out of the piece. So this was just easier to manufacture as one constant thickness width.
Okay, that's, I mean, especially given time constraints, where this is a redesign, that's a reasonable answer. And it sounded like you were well under your weight target, maybe even a little too much under your weight target, given that you had higher speeds and flutter, which I'll come back to in a minute. But also, speaking of weight, right, you said that you had to adjust your CG by adding 13 ounces of ballast to your design, right? And you're talking about, yeah, you're talking about an aircraft weight on the order of what, like 6.5 pounds? And that's, is that including the ballast?
Yes, that's including the ballast.
Okay, so you're talking about, I mean, that's almost a pound of ballast, right? So from 5.8 or so to 6.5 pounds, you've 20-ish% of the weight of your airplane is just ballast, right? Like how did we miss that much on the CG?
It was a combination of not paying attention to the size of the nose in comparison to the position of the wing, as well as not considering the amount of weight located on the empennage and the effect it would have on the overall CG.
Okay, so was your CG too far back and you ballasted the nose, or too far forward and you ballasted the aft?
It was too far back, so we balanced to the nose.
It was originally without the weight, it was at like the half chord point. Yeah, we wanted to move to the quarter chord.
Okay. Were you one of the, I forget, from a month ago, were you one of the teams that said you had some ability to adjust the CG by moving the location of the battery?
Yes.
I'm guessing that you didn't have enough motion in the battery to get your CG where you need it to be?
It was as far forward as it could go. It's simply, we just needed to make the nose longer. That was the only option. Which what we did, that's exactly what we did for the second flight. We just added an entire new section to the fuselage, and then we didn't need the weight anymore.
Did that get rid of the need for the ballast then?
Yeah. And then the battery was as far forward as it could go, and the CG was right where we wanted it to be.
Okay, excellent. Let's see. So so Flutter. I think you guys are the first time. I've been doing these for a couple of years now, and I know that Ting has done a couple of different RC airplanes, and you guys are the first ones that I've seen have an issue with Flutter. So I know you said your speed was higher than you were anticipating, and that can certainly cause those sorts of issues. But did you do any sort of analysis to say, okay, we don't expect to have flutter at the speeds that you were initially predicting? And do you have a solution for that other than fly slower?
We did not have any predictions for flutter to my knowledge. The particular cases where flutter came through, it was during a maneuver where I went from high altitude to a low altitude-ish pass, where I gained speed by trading altitude. And that was a much higher difference than I was expecting because I was also at higher throttle than I should have been. So combined, those made for higher speed, which had higher flutter on this left aileron.
One issue was our wing was like not stiff. So like we don't have a spar that goes through both wings. Like there's a spar that goes through the one wing and the spar that goes to the other wing. So before our flight, we try to like lift the plane from the wingtips and like the fuselage wouldn't go up. So there's like, it wasn't like a stiff, it wasn't enough, it wasn't stiff enough. And we didn't do any like analysis for flutter, but we should have kind of realized that a lot of things weren't really stiff in our plane. So by going faster, we just encountered it.
Yeah, the rear control surfaces on the elevators, those do have mechanisms to prevent flutter, but those are not present on the main wings ailerons.
Okay. Okay, that's all I've got for now.
Thank you, Tom.
Thank you.
Thank you.
So overall, great job. Congratulations. Just some details. One thing is not really a question, just like you said, if the buzzer would use the laser cutter, what did you guys do?
I used the FTC, I used the DBF laser cutter. too.
Oh, that's cool. Is it expensive?
I think it was like $900.
Okay, I'm not gonna buy expensive my class. I don't have that money. So. And one side you showed, you use different, you have the metal gear servos, you have the plastic gear servos, you have the like 9G, 17G. Do you have any analysis like justification why use different thing at different different place?
I know for the one of the 9G servos, which was going to be located on, we relocated that to the elevators. That was because of space issues with the current prototype. For the 17G servos, I think some of them.
It was the horizontal tails didn't have as much room as the vertical tail here, like width-wise. So we just had a smaller geometric shaped.
So the selection of 9G or 17G is just for the space.
Yes.
Okay, it's not because like it's larger force required or something.
Nope.
How about the metal gear and the plastic gear?
Long.
What?
We already so long ago.
You guys engineers.
What we received was about 8 of the 17 Metal Gear servos. So did we even have any plastic?
No, we did not have plastic.
I don't think we had any. I think we
But
had them
why
in
is
the
it?
purchase order.
This is plastic.
Yes, it does say plastic, but
This is
we,
plastic.
for only the 9G, the two 9Gs were put in for the elevators.
Okay,
And then the 17-gram Metal Gear ones were put for.
okay, you guys didn't use the plastic.
No, we did not. We ordered them, but we didn't get any. We just used metal ones, which isn't a
Should tell me
big.
because order I pay the money, we should have it.
Oh,
Yeah, if you tell me, I can ask the Amazon or anything, I don't know. And one thing that in the structure analysis is like, I don't know. So you have I think, purely for the first for the material, I think you guys use operative wood for the
yes.
and also for the balsa wood for the stringers. First for the material, why use different type? I mean, give me justification.
So for the poplar spars, that was because of ease of access through retailers such as Lowe's and Home Depot. And then for the stringers, it's easier to bend the stringers when shaping them into the ribs so that we can have diagonal stringers, so we can have a little more structure to the planes. So we just found it a little easier to bend. And then
Also, it's super lightweight overall. Poplar's a little less light and a little more stiff.
Okay. So in the calculation, I remember in one size, is think it's this one, yeah. The popular wood, you put arming strength there, and in your calculation, I believe you use this one for your calculation, but you should know that that wood, that rod is at the center. But actually your stringer is at top and bottom surface. So actually the one that carry the bending, the normal stress cause of bending is the stringer, not the one around neutral surface. Do you agree with me?
yes.
That's why in your calculation, you should not use arming strength of the poplar wood because it's not really carrying any normal stress cause of bending. It's at neutral surface. And the stringer is really at top and bottom. So probably there's some calculation mistake, right? And I think there is one slide, it says torsional bending. Sorry, I didn't wear my glasses, so I cannot see the page number.
Yes, torsion. Yes.
Well, it's fine. So I think it's like one side you said torsional bending to prevent the something sliding out of the connection part. I mean,
Tabs.
yeah. I feel why torsional bending? I mean, that is pure bending problem, right? Torsional will not make your the contact surface like connecting place like sliding out is bending. And also, I really don't know what torsion and bending means. I mean, torsion, bending, bending. So, first, if you want to prevent something sliding out, is from bending, it's not because of torsion. Torsion is rotation. So just make it like more accurate in your final report. And the other thing is the tension wire for the landing gear. Is that plastic or something?
Fishing wire.
Fishing line.
Do you think that's really provide any strength, like to prevent?
Like 80 pound.
It's rated for 80 pounds.
80
So
pounds.
So without it, it would actually like.
it would
Yeah,
try
we
to
just did
spread
some
out.
Oh,
and we had the wire not on it.
I don't know what we did though.
I was like surprised because it's like plastic applied can actually prevent.
It helps prevent it from slouching when under its own weight. I think like a big one when someone was taxing off, it wasn't going to be able to like be more of a give more of an incident angle that wasn't
Yeah.
intended for the plane.
Okay.
Yeah, we did ground testing on the old design, and at that point, of ground testing, we did not have the wire.
It's a closed door because I booked this room until 7 or 8, so we can ignore everybody outside.
I think it's quiet now.
Yeah, closed door. It's outside. So sorry.
So we did ground testing without the wire on the first iteration of the landing gear. And during that ground testing, we did we pushed on ends of the plane. That's where we discovered it was wobbly. But that's where we also discovered that you could in fact bend the landing gear just by pushing it. So that is one reason why these structural improvements helped.
I'm just so surprised that fishing line can help. I mean, whatever helps, it helps. But just like for me as an engineer, I will always want some analysis. So a plastic line, so thing. But I'm glad it works.
Fortunately, we didn't get to see it work.
No, they saw it work on the takeoff rule. Takeoff rule. Gotta survive the crash.
That's the only thing that survived.
The landing.
Yeah, whatever works.
Yeah.
For me, I just want to see something like really analysis behind it. So I mean, because for me for now, it's hard for me to understand like so thing it actually work, but it works. So for the I think it's same question as Tom. So you guys so you did the presentation of the part of the second test slide and you put all the fault to you instead of design problem.
Yeah,
appreciate that. It's
I
like
thought we were pointing one direction when we were pointing the other direction, and I overcorrected.
yeah. So what I want to say that is it really pure piloting problem or is there any design problem caused flutter? You said it's purely caused high speed. It's really like because of high speed caused flutter or is some design thing that caused flutter? That's what I want to know.
There is a consideration of the gap between the back plate of the wing and the control surface.
This type right, this is not accurate since I pieced this back together, but this is kind of what the gap is that what we're talking about.
So the original
Is it a large? Is it going to be would it be a larger gap here?
yeah, I mean before the second test flight. You said you put this one back after the second test flight.
Well, yeah, because this broke on landing, so I just put this back
But the
together.
original gap is like larger than this one.
I don't know if it was a larger gap or not, but it's probably around a similar size.
Okay. Okay. So I don't know. I'm not an expert. So I just want you guys to do some research like what actually caused flutter. I don't think it's 100% because of piloting skill or high speed. It's not like 1% his fault. So in the final report, I hope that you guys can do some research like what is it really any really pure which
In part to the lack of stiffness in the wing that may have caused.
yeah, that one I was actually research when you guys like
Yeah, it was especially noticeable only on the wings and first the thickness.
yeah, maybe it's a stiffness, maybe also it's like I saw you guys like do the CG test. I was like I was really scared. Or it's like in that process, maybe something was broken inside because it was like very scary. When
You're gonna have a skin fracture and
yeah, maybe something
I think I heard a crack during that. Yeah.
Or it could have been the spar itself on the other side, on the other wing, where the whole wing
Yeah.
sheared off, the wood was broken and just completely ripped.
Yeah.
It separated, the wing separated from the fuselage, the rib broke, the wood broke, bolts are gone.
Yeah.
Brought us that
The
way.
thing in the design that you put the much thicker rod in a neutral surface, which does not carry much, and you put much thinner rod to the bottom and top surface, which is high stress surface. Right? So if like if you guys we're done with this semester, but just like something in future, you guys engineer, you would do some similar thing in the future. Just like wherever higher stress, stronger structure. Neutral surface is not really necessary, right? So I feel like if we have that much like so thick at top and bottom, you probably wouldn't happen like when you do the CG test, right? So
Good point.
Was your wing box continuous structure or between the wings? They were separate.
The spars.
You think that, yeah, so like you're, yeah.
That is something that Harris.
Like flapping wing.
Yeah.
You think that could be,
Definitely.
Otherwise, your voice will not.
do you think that that could have been a major like problem in terms of the CG thing?
In terms of CG.
Not the CG, sorry, the CG test, like when we were. Yeah.
Stiffness.
Um,
Bar structure.
Yeah, I would say that it could definitely probably significantly improve
They could
the
have
structure.
put something in there and glued and fastened them together, but getting a 6 feet long piece of wood while monocoating both sides, getting it through the fuselage would be a big pain for manufacturing.
Yeah.
So the only option, would have been, splicing something in there, which we did do for the empennage. The 2 horizontal ones were glued to more wood around it.
Something such as like a pen would have been helpful in addition to the press fit.
So I think earlier, it might have been you, Brendan, who mentioned this. I don't know. Correct me if I'm wrong if it wasn't you, but somebody, I think it was you, mentioned stability from pilot input. How reliable is that? And like, what kind of stability are you talking about from pilot input?
So if this is from when I was flying.
Slide 6, if you want to go back to that.
Slide 6.
Oh, yeah. So basically, as we had in stability analysis, that was where we had the more concern about phugoid and spiral modes, where like if the pilot would notice phugoid, that's easy to just resolve, or spiral, that's an easier quick because of like the time over which it elapses. The pilot response time is much quicker than the period over which it occurs.
Okay, so you're specifically targeting like the roll divergence, right? Like the one where it's like 2 minutes long.
Exactly.
Okay, just making sure. Let's see. So you showed on slide 7, I feel like that figure on the bottom right is a little hard to understand if you hadn't seen it before.
Yeah.
And I also have a question about the control horn. Why is it designed like that? Why, what's the shape for? Like, is there a specific reason?
This is to provide the control horn like maximum deflection without being as close to like being able to accommodate like various lengths of control rods.
Okay.
So we couldn't like ensure that each control rod was going to be of uniform length, which it wasn't. So since some of them required, since they were so short, required them to be this to be closer to the edge of the control surface. This helped make it be able to reach the control rod and be able to have maximum deflection.
As we had to during manufacturing, we had to like move them around, rotating the servos or hitting them on different points.
Okay.
Sometimes they broke.
Yeah, that's it.
We did address the servo stuff, so we got that. Okay, slide 17. John, I believe you mentioned something about the ultra coat being like lighter and cheaper and easier to
Easier to
use. Like,
manufacture, for sure, yeah.
so
I mean,
how much cheaper? Like, do you have a metric that you compare between lightweight delay? And also, sorry, one other question about the weight. Like, what weight savings did you get or anything like that between this and?
Well, the Ultra is almost a negligible weight. It's a very thin layer of plastic. The whole thing's probably like less than an ounce, right? Yeah, for both wings. And
How
so
about cost?
the whole one roll was like
$18.
$18.
I think that's what I bought. It was about 36 for 2 rolls, which was the total cost to manufacture
the roll PLA is also like $20. I bought some for like $18. So in terms of manufacturing that, like, well, probably both wings might have been about a roll, maybe. So
So you guys didn't necessarily have a metric because it's just because you were saying it's cheaper, but like how much would have been a nice way to kind of like put it and be
Mhm.
like, oh, well, like this much square footage or whatever of PLA is this much or something.
Yeah, actually,
Because
I have
it's
the same
cool.
question. Yeah, I have the same question I didn't ask. So it's like, let's say I give you a chance. So this is the first I really appreciate in my class that we have the, I know TBS like to use this one. And like previously we have the carbon fiber, we have used the film core, or we used to wrap around the 3D printing or like PA or regular PA. So now I give you a chance. Compare your design, your manufacturing with group with like regular conventional carbon fiber manufacturing with film core, high density film and carbon fiber wraparound, or the carbon fiber wraparound, the 3D printing part, or printing with purely regular PA or light PA. Why yours is better?
So I believe that kind of monocode is the best one. This wasn't like a purely best optimized monocode wing.
If it's your choice for your design, you should say the best.
I believe it's the best just because it is, in my opinion, the most lightweight option. The best way to design a monocoque wing in traditionally would be to use balsa ribs along with instead of the 3D printed ribs, and as well as making these control surfaces balsa. But that would be requiring more time and a little more specialty in terms of manufacturing, which our team didn't have entirely. So we opted to make some of them out of a 3D print, which somewhat decreased the benefits of monocoque, but I believe the benefits that introduced through the ability to attach the servos easily into the plane without compromising skin structure. And some of the failure videos that we watched earlier in the year showed that failures through the cracking in the skin through the servos, and we thought that this was a good way to avoid it, as well as being able to make slight adjustments in the plane. And it also allowed us to make our fastening mechanism that we chose for this wing a little easier to access, since we would be able to cut open to access any issues, or if anything broke, or if anything came loose, it'd be easy to remove it and maintenance it as it.
I guess that maintenance would probably be the best part, like especially compared to carbon fiber PLA skin. Like we had our flap servo wrong, and it's very easy to cut open and retape, and we still had a fully functional wing. Whereas if we had something 3D printed or carbon fiber, we wouldn't. Yeah, you'd have to completely reprint the wing or completely recoat the wing, and instead we could just cut and tape.
Yeah, we did
Exactly.
it
During our
for
first
servo.
system spec,
Yeah.
we had to rotate some servos, which would not have easily been possible if this was not able to just be
Yeah.
cut open and retained.
It was able to be moved 2 servos, or flip 1 servo and move 1 servo. It was able to be done in like, I think I did it in like 2 hours versus how long would the prints take? Days? Yeah.
So I hear a lot about manufacturing, and that's great. And like I think it is really cool that you guys decided to go with something different.
It was fun to make too.
PLA. Yeah, you guys essentially really did like build a plane. That's how you build models, right? You have a spar, you got whatever ribs and stringers and stuff like that, and then you skin it up, right? That's really cool. But the only thing that I think that Dr. Ting was addressing that I still didn't see out of your answer just there was like, to what extent is it more like efficient in terms of weight, cost, all that stuff? And having a metric would be a great way to show the customer, like this is like actually superior to whatever else in terms of blah 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 blah.
Yeah, probably something like in your final report, like trade study. So we have different options, 3D printing different filament, like PA, regular PA, or carbon fiber conventional method, or like carbon fiber wraparound. And we compare the strength, the weight, the cost, manufacturing, or anything you can imagine, and put like something as this and okay, conclusion, we choose this one.
So I think that comes to a weighting of manufacturing, well, not manufacturing, but of parts cost, labor cost, and what was I gonna say? Parts, labor, and something else cost, weight cost.
Yeah, we could do that for the
Yeah.
final report. I think that's
Yeah,
definitely
yeah,
achievable
in the final
before the
report.
day.
Okay, so let's see. I saw sharp corners on some hatches on fuselage.
Those were changed.
Okay,
Those were-
you were changed.
That was a old
All right, I
iteration.
might have missed that in the presentation if you addressed that.
I don't think we did, we clarified that, but
Okay.
it was, when we reprinted to accommodate for the ribs and stringers in there, those hatches were all changed.
That's
Both of
pretty
these
good.
hatches on the remaining fuselage pieces
Yeah, if you wanna,
are the new
it
design,
out.
which these are rounded hatches.
also, they're all taped over too. All the hatches were taped down before flight to hold them, to fasten them.
Did we consider like slide 21, you guys were discussing your pallet? So you guys said that you mounted the top of the battery. Did we consider any effects or any kind of like concerns about mounting it to the top of the battery?
in terms of like electrical effects.
Yeah, I mean,
Like,
what if this increased weight on the battery caused the battery to dislodge? I mean, are there any safety measures to prevent the battery from?
The only safety measure was, I believe you taped the battery as well as put Velcro on the battery as well, so it was taped and Velcroed. And I think the only concern from my end would be heat transfer from the battery to the container itself. But there was a vent hole used for the wiring that was directly in the way of the container.
Yeah, so yeah, you did take like a secondary step, you take the battery down, so that's good, because I was concerned that maybe it would move, but obviously it didn't.
Yeah.
Like, but I'm just addressing it.
Valid.
And then, okay, so we discussed slide 22 on the takeoff that you guys didn't actually take off with the runway, you instead took off like what I heard was perpendicular.
Yeah, the taxiway, we were on an angle to the taxiway directly into the wind.
Well, did we consider, or did we like calculate it? Could we have made it? Like, did you just send it, or like, were there any calculations before?
We sent it. I did not want to fly that day.
And the reason why I kind of bring this up was because your landing gear, your wheels are really small. So to me, that indicates that you weren't planning on taking it off-roading. So was there a consideration on changing the wheel size, or why small wheels as a choice?
There was a consideration for the second prototype to up them to 4 inches to accommodate this the new landing gear structure. I believe in consideration of time to get a second flight, I think we decided to just send it for the second prototype. But that would be a good option for off-roading.
For bush plane style landing.
Okay. And then another thing about the flaps, like I didn't fully understand why you guys chose flaps. Like I didn't see that, or I didn't get that message wasn't conveyed on why you added the flaps. What does it actually do for you? Did it reduce your takeoff roll by this much, whatever? You know, I didn't kind of understand why you added flaps. So like, was there a significant need for the flaps? Like, what did it give you to add flaps to the airplane?
During test flight 2, when we didn't have very much wind to help us take off, but we had the flaps enabled for the takeoff, which the takeoff was pretty long on its own. And without the flaps, I think it would have been longer.
Okay, that's different than mathematical stuff. So like, I'm talking mathematics stuff. If you guys have that, definitely include that into your report, saying like the flaps allowed us to take off at this speed in theory, right? Obviously, it's probably different in real life, and shorten up our takeoff roll, and that's why. Therefore, it's justified. Right? We have a justification why we add complexity to the system, and then. Okay, we discussed about the surface flutter, the left aileron fluttering. Okay, that's all I have. Yeah, if you have anything.
I think everything I had got addressed already.
Yep. Otherwise, great job. Great presentation. And glad it flew. Yeah, it did fly.
Wait, video. I sent a message there time. I also talked yesterday. I still didn't have the
The second flight.
second.
We're just kind of want to keep down the most as we can. I can send.
One day I will become a YouTuber with 1,000 subscribers. I think people will become like very famous, very popular.